Welcome to the last section that we're going to discuss in Chapter 12, and this section is called Equations of Lines and Planes. And so what we're going to be finding is we're going to be finding the equations of lines and the equations of planes. We're going to talk about how we get the equations of line and planes, and then talk about their necessary uses. And so a line L in three-dimensional space is going to be determined when we know a point, x sub 0, y sub 0, c sub 0, so an initial point on L, and the direction of L. In three dimensions, the direction of a line is conveniently described by a vector. So we let V be a vector parallel to L. A vector equation of L is, and then we have R is equal to R sub 0 plus T times vector V. All right, so basically to put this in another way is that, when we're trying to write an equation of a line, when we were working in two dimensions, you could do an equation of a line pretty easily as y equals mx plus b, where b was your y-intercept or an initial point, and x is your variable as you're going along, and your m, that is your slope. And we're able to, talk about how we have a line now in the two-dimensional plane. Well, that's a very similar concept to the equation of a line. All right, the equation of a line, so our line, all right, is going to be given by, this vector r, where we have an initial point, all right, where we need an initial point, and then we need a slope. But in this case, what we need, instead of having a slope, we need a vector that's pointing in the same direction as our line is. So our vector is parallel to that line. So vector V is going to be parallel to whatever line that we're using. All right. And then T is like time as time goes on. And so basically what we have, this equation, this vector equation of our line L, our equation of our line is a very similar concept to our slope-intercept concept in the two-dimensional plane, where we start off an initial point and then we grow, but as we're growing, instead of having a slope, we have a vector. All right, so hopefully that's, an easier way to see the vector equation. All right, and so now as t varies, the line is traced out by the tip of the vector r. The vector v that gives the direction of line L is written in component form, and so we have v with its component a, b, and c, r its components x, y, z, and our initial point x sub 0, or initial r x sub 0, y sub 0, z sub 0, then, we can write the vector equation in terms of, parametric equations, where we can have our x, we can have our y, and we can have our z. And again, these all can be written out as their own equations. So these equations are parametric equations of the line L through the initial point and parallel to the vector A, B, and C. And so what we're going to do is we're just going to find the vector equation and then the parametric equations for our line. And we're going to be given a point, and it's going to be parallel to our vector. So let's go ahead and write down what our initial point is. So our r sub 0 is going to be our initial point. And so we're going to take our initial point like it's going from the origin. And so our r sub 0 is going to be 6, negative 5, 2. Our vector, all right, our v value is going to be, put that. We can go ahead and keep this in standard basis form. We can just go ahead and change to 1, 3, and negative 2/3. And now I have everything that I need to go ahead and write my vector equation, or the equation of a line. So r is going to equal, and here I'll write out this just so that you can see it as I'm writing it out. And so now I'll change the color. And so r is equal to 6. I'm going to go ahead and call this, I'm going to write this in standard basis form. 6I minus 5J plus 2K, and then plus T times I plus 3J minus 2/3 K. Sorry about that. There's something on the screen. And then now I can go ahead and combine my components together. So everything that has an I term. So I have 6I plus TI. So I'm going to write that as 6 plus T. And this basically right here is going to be my vector equation. But I'm going to clean it up a little bit. And so then I have, let's go ahead and say plus -5 plus 3TJ. So again, that's just coming from combining all the terms with J in it. And I can't forget, I have to distribute that T. And that's how I'm getting -5 plus 3T. And then plus, now my component with K is 2. So 2 minus 2/3 T. Okay. Alright, and again, both answers will work, but this one's just a little bit more simplified. It has all the components tied together. But again, the first equation works for the vector equation. And then we want to put this in terms of parametric equations, which isn't going to be bad. X equals 6 plus T. Y is equal to -5 plus 3T. Again, you could write that 3T minus 5. And Z is equal to 2 minus 2/3 T. And so those are the parametric equations. Alright. Now, one thing that you need to notice is that if none of A, B, or C is equal to 0. So when we have our actual, vector equation, or not sorry, but our actual vector V, and so for our values A, B, or C, so we're talking about this vector. So for our vector V, if our values are not 0 for that vector, any of our values, then we can solve each of these equations for T. And it's going to equate the results and obtain a symmetric equations of L. So basically, we can take all of our equations right here, our parametric equations, and we could solve all those for T. And if we solve all those for T, what we're going to get would be symmetric equations, because those are all going to equal our T value. Alright, one more thing I want to add to this is that if we're ever given our symmetric equations, one thing I want you to notice about the denominators is that the denominators, A, B, C, are our vector equations for our equation of a line. Alright? So if you're ever given something in symmetric equations, just know that the denominators are going to give you your vector V.